Hello, in this video we're going to explore the derivative and antiderivative of y equals e to the x. So first thing to consider, um, e, by the way, by definition, or one of the ways to define e would be the limit as x is going to infinity of the quantity 1 plus 1 over x to the x. And e, by the way, is called Euler's constant, after Euler, mathematician. And just to convince you that's, actually I should say that's about 2.718. It's an irrational number, doesn't repeat, has no pattern, doesn't end. But just to show you that is indeed the limit, I've set up a little note here, 1 plus 1 over x to the x. And so I'm going to kind of think about this limit graphically and just show you that it does indeed work out. So what I'm going to do is I want x to go to infinity, so I'm going to set up my table so x is going to get wicked big. And start big and get bigger by hundreds. And so if I then go back into the table of all the values for 1 plus 1 over x to the x, note that as x is getting wicked big, it's approaching infinity, the y values are heading towards a number that looks about like 2.718. Okay, so that's just an illustration, not really a proof, but just a demonstration by calculator, if you will. The graph of y equals e to the x has some characteristics which we've started to talk about, and we don't need a calculator, but we'll do it anyway. The graph looks like a basic exponential, the positive base function, and this doesn't stop here. Okay, it has an asymptote y equals 0, so I'm going to just exaggerate that a little bit on my rudimentary graph, and it goes for the point 0, 1, because e to the 0 equals 1. Okay, and that's what e to the x looks like. As x is going to negative infinity, the limit is 0, therefore has a horizontal asymptote y equals 0. Gets closer and closer to 0 as x heads towards negative infinity. Okay, positive range, all real domain, blah, 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 blah. But what we have not yet looked at, however, is calculus pertaining to anything exponential. So let's start with the derivative of e to the x. Now this is fascinating because what we'll find is that e to the x is its own derivative. So to establish that, I'm going to use a limit definition. So actually let me use good notation. So the derivative with respect to x of y equals e to the x is, by definition, limit as h is going to 0 of f at x plus h minus f at x, which would be e x plus h minus e to the x all over h. Remember this guy? That's called our difference quotient. And we're taking 2 points, say here and here, and evaluating the slope between those 2 points. All right? But we want the h to go to 0, which brings the 2 points wicked close together and turns the difference quotient, which is in blue the slope of the secant line, into the slope of the tangent line, the instantaneous rate of change. All right, so now I want to execute this. So the limit as h is going to 0. I'm going to factor out on top e to the x, and this is what I'm left with. Right, you pull in e to the x plus h. Remember, another way of saying e to the x plus h is e to the x times e to the h. You add the two exponents. And now the limit as h is going to 0 has nothing to do with e to the x, so I'm just going to pull that out. Okay, and what I am left with is the limit as h is going to 0 of e to the h minus 1 over h. That h is too big. Okay, so I need to evaluate this darn limit. And quite frankly, it's one I'm just going to show you. Proof by calculator. Not a legitimate way, but I will show you that limit might be perhaps 1. So I have graphed, instead of e to the h minus 1, it's e to the x minus 1 all over, instead of hx. Because you know our calculator can't do h's, nor would I need it to for this case. So I want to evaluate the limit of this guy up here as x, or h, is approaching 0. And remember, in this case, my x's are my h's. So I'm going to do that by table. I'm going to go in here and put the table at 0 with a small change, about 0. And I'm just going to look. Proof by calculator. And note that the left and right-hand limit, as x is going to 0, seems to agree and appears to be 1, and it is. So that blue limit is just 1. right? Therefore resulting in e to the x. It's its own derivative. So pretty cool. So the derivative of, with respect to x, e to the x is e to the x. It's its own derivative. Aside from the trivial function y equals 0, I'm not sure of any other function that is its own derivative, although I'm sure there might be some. Um, Again, because the derivative e to the x is e to the x, that means the antiderivative moving in the other direction, the antiderivative e to the x with respect to x will be e to the x plus some constant of integration. Okay, so we're kind of establishing both directions, differentiating and integrating, anti-differentiation. So this is what we come up with. Okay, so that said, I have two questions for you to consider. Okay, and these are your homework problems. Number one, questions. Questions. And they both, of course, pertain to y equals e to the x. Okay, number one. There's a tangent line at this point, 0, 1. What is the equation of that tangent line? Okay, and remember, tangent lines could look like this, right? Where m, the slope, comes from the derivative of e to the x at 0. Okay, question number 2. What is the area from 0 to 1 under the function? In other words, what's the value of the definite integral from 0 to 1 e to the x dx? Okay, so question number 1, we're going to find the equation of the tangent line of this guy. In question number 2, we're going to find the area from 0 to 1 underneath the function y equals e to the x, noted by this definite integral value. Okay, we'll talk about these answers tomorrow. I hope you have a y equals excellent e to the x day. Bye-bye.